All right, today we're tackling something massive. Literally, the fundamental reason why atoms bond and why matter even exists as we know it. We're going to explore this core principle that basically governs the entire architecture of our universe. Seriously, it's a wild story full of atomic desire, absolutely perfect trades, and, yeah, a few pretty rebellious rule breakers. So we're starting with the ultimate question about your very existence. Kind of a big deal, right? It frames the universal problem that nature had to solve. Think about it. If atoms are the basic building blocks of everything, why don't they just stay by themselves? Why go through the hassle of joining together to form water, or your DNA, or even the screen you're looking at right now? Well, the answer to why you aren't just a chaotic cloud of independent particles comes down to one thing: a relentless, nonstop drive for stability. And honestly, the solution to that drive is elegantly simple. It's just a number: 8. Now, I know it might seem like just another digit to you and me, but in the atomic world, 8 is the absolute holy grail. It's the finish line. Let's look at exactly why that is. All right, moving into section 1, the quest for stability, or as I like to call it, the Grand Hotel. So I want you to picture every atom in the universe as a restless guest trying to check into the Grand Hotel of electrons. Now, obviously, not all rooms are created equal, but every single guest desperately wants a full room. But then you have the VIPs, the noble gases. Helium walks in with 2 electrons, boom, its tiny room is already full. It's perfectly happy. Neon arrives with 8 electrons, full house. Argon, same exact deal, 8 electrons. They literally do not need to interact with anyone. When scientists first notice these noble gases, they realize their secret. They're already perfectly stable because their outer electron shells are completely packed. So here's the absolutely crucial point. Every other atom in the universe is desperate. They're highly reactive, and they will do whatever it takes to achieve that magical state of 8. Sodium, chlorine, oxygen, carbon, they all arrive at the hotel with incomplete rooms. They're totally restless. To finally find that stability, they're going to gain electrons from a neighbor, give them away, or even share them, all just to mimic those VIP noble gases. And that right there is the Octet Rule in a nutshell. Which brings us to section 2, the magic number 8, and the math of stability. Now, what's really interesting here is that this isn't just some random preference. The basic orbital math is brilliantly structural. In an atom's outer shell, there's an s orbital, and that holds exactly 2 electrons. Then you've got p orbitals, which hold a total of 6 electrons. Do the math, 2 plus 6 gives us that perfect 8. Completing that outer layer of the puzzle drops the atom into a much lower, way more stable energy state. And uncovering this was actually a fascinating historical detective story. Picture this. It's 1916, and you've got 2 scientists staring at the periodic table, completely independently unlocking the secrets of molecular architecture. Over in the US, Gilbert and Lewis noticed these patterns that led him to propose that atoms share electron pairs to get to 8. You know, this actually gave birth to those Lewis dot structures you probably spend hours drawing in the lab. Meanwhile, over in Germany, Walter Kossel figured out that atoms could also just completely transfer electrons to get the exact same result. 2 brilliant minds, separated by an ocean, cracking one incredible rule. Let's dive in to section 3, how atoms make deals, and how they actually solve this puzzle. Okay, a really great memory trick for your exams, and you'll want to write this down, is that Lewis means sharing. We call those covalent bonds. Kossel, on the other hand, means transferring, which we call ionic bonds. It's like this. If one atom has an extra puzzle piece and another is desperately missing one, they just transfer it. Boom, problem solved. But if both of them are missing pieces, well, then they sit down and hammer out a sharing agreement. Take ordinary table salt, for example. It is the absolute perfect trade. Before the bond, sodium is sitting at 281, meaning it's got one extra lonely electron just hanging out in its outer shell. It's highly unstable. Chlorine, meanwhile, is at 287. It is agonizingly close, just missing one single electron. So sodium eagerly gives its extra piece away, and chlorine happily grabs it. Now sodium drops down to a completely stable 8 mimicking neon, and chlorine bumps up to a stable 8 mimicking argon. Literally a win-win transfer. But hey, transferring isn't the only way to play the game. Let's look at sharing agreements. Oxygen is missing 2 pieces, right? So it shares electrons with 2 hydrogen atoms to complete its puzzle, which gives us water. And then you have atoms like carbon. Carbon becomes an absolute social butterfly. It's got 4 valence electrons and needs 4 more. So it shares pieces with 4 different hydrogen atoms at the exact same time to achieve stability. This creates methane. And honestly, this unique ability for carbon to share so widely, it's literally the foundation of organic chemistry and, well, life itself. But nature isn't always so orderly. Welcome to Section 4, the rule breakers, and the exceptions to the rule. Now, listen up, because professors absolutely love to test these 3 exceptions. They prove that some elements just do not care about the number 8. First up, we've got the incomplete octet. Elements like hydrogen only ever want 2 electrons. That's called the duet rule. And boron? Totally stable with just 6. Then you have odd electron molecules, where the math just straight up doesn't divide evenly. And finally, the expanded octet. This is where larger atoms actually have access to d orbitals and basically act like VIP suites, holding 10 or even 12 electrons. Let's actually see how these rebels look on paper. Take boron trifluoride. Count the dots around that central boron. There's only 6. It's totally electron deficient. But hey, it exists and it's perfectly stable. Then look at xenon tetrafluoride. That central xenon atom is packed with 12 electrons. How? Well, because xenon is further down the periodic table, it actually has the architectural space to expand way beyond our magic number 8. Now let's circle back to that middle exception, odd numbers. It is kind of mind-blowing that just having an odd total number of valence electrons, like the 11 in nitric oxide, means someone is always left with an unpaired piece. It's literally mathematically impossible to fill the octet. We call these molecules free radicals. And because they're missing a partner for that lone electron, they are incredibly reactive. They just run around trying to steal electrons from other molecules. It's a crazy process that's actually responsible for both atmospheric chemistry and, get this, biological aging in your very own cells. All right, moving to our final part, Section 5, limits of the model, or where the map ends. So look, while the Octet Rule is basically chemistry's Swiss Army knife, it's brilliant for explaining ionic and covalent basics, and it's great for predicting broad reactivity trends, it simply cannot explain everything. It completely fails for transition metals like iron or copper. It gives us absolutely zero information about 3D molecular shapes, and it totally misses the boat on complex behaviors, like the fact that liquid oxygen is actually magnetic. No way the Octet Rule predicts that. So I want you to remember this analogy because it really hits the nail on the head. The Octet Rule is like a map of a city. It's going to help you navigate most of the main streets perfectly. It gets you from point A to point B in standard chemistry without a hitch. But it won't show you every hidden alleyway, every shortcut, or every underground tunnel. It's an oversimplified model. A fantastic, incredibly powerful guide to why atoms bond, for sure. But it is not the absolute, complete reality of quantum mechanics. So we've mastered the rule of 8, we've met the chemical rebels that totally break those rules, and we've mapped out the limits of our model. This rule does an amazing job explaining why matter holds together. But knowing what we know now about where it falls short, it leaves us with this really exciting question. Are you ready to ditch the basic map, dive into the actual quantum shapes of these bonds, and explore the underground tunnels of molecular orbital theory? Because honestly, that is where the true, weird, and wonderful nature of the universe is waiting to be discovered.